All right, everyone. So in this video, I just want to talk about and clarify limited domains for us, or how to find domains of functions algebraically. So just keep in mind that most functions will have a domain of all real numbers, which can be interpreted using the interval notation negative infinity to positive infinity, with the exception of functions where the input value, right? Remember, your input values come from the domain. Causes either division by zero or even roots of negative numbers. So even roots can be like square roots. You can't take the square root of a negative number in the real number system. So with that being said, anytime you see like a division by zero or even roots of negative numbers, those values, those input values, you must take it out of your domain. You must pull them out. It's like, okay, you're a bad guy, I'm pulling you out. All right. So here are some examples. If you look at this first example that I'm about to write on the board, or write out, if I have f of x is equal to 3x squared minus 7x plus 11, right? I'm just making an example up here. We said this earlier, but what type of function is this? It's a quadratic, right? This is going to be a quadratic. Now, for your quadratic function, is there going to be a value of x that causes a division of 0 or a even root of a negative number? Well, first of all, does it look like do I have any fractions here? No. Do I have any roots here or even square roots involved? No. So this quadratic function is basically clean. It's clean in the sense where it doesn't have any problematic inputs. So our domain is all real numbers, which again, you can that would be it, the domain in plain English, but the interval notation will be negative infinity to infinity. Right, so that's my first example, and it was quite basic. It was just showing you that, okay, if I have some sort of function like a quadratic, if I don't see any values of x that can cause division by 0 or a square root involved of a negative number or even root of a negative number, it's clean, no bad guys, domain is all real numbers. But let's now look at functions where you have these bad guys. Let's say if I have g of x is equal to 5 over x minus 4. Can you identify or pinpoint a value of x that you can say is a bad guy that we have to eliminate? Can you pinpoint a value of x that essentially looks like a bad guy? Why you say 4? No, not that. No. Yep. Look, okay, so we got a little distracted. Let's bring this back. So I have g of x equals 5 over x minus 4. So my question is, what value of x, is there a value of x that we can consider a bad guy, somebody that we can eliminate from our domain? The answer to it is yes, right? Because if you look at this expression, it's a rational expression, or it resembles a fraction. Well, because it resembles a fraction, look at the look at our reasoning or causes for eliminating or excluding a value, an input value. If you have a division by 0, there is going to be a value of x that makes that denominator 0, right? If you just set the denominator here, x minus 4 equal to 0, you can figure out who's the problematic input, right? If you solve this equation, what do you get? Solve that equation, x minus 4 equals 0. X is equal to 4. There you go. So this value is not our answer per se, but we say that that's our problematic input. Problematic input. So because it's a problematic input, you have to remove it from your domain. Okay? And if I'm removing it from my domain, I can interpret my domain in three ways: in words, graphically, and interval notation. Okay, so graphically, in words, since the name of this function now is g, I'm going to say my domain of g is all real numbers except, very good, except when x is equal to 4. Visually, if you look at a number line that starts from negative infinity that ends to positive infinity, you can pinpoint the location of 4 here. Let's say somewhere around here is x equals 4. Now, because 4 is being excluded from our domain, if I want to show it visually, I use an open point. I can use an open point, and I can take any value of x to its left, and I can take any value to its right. So how would I write out the interval notation? The interval notation comes from the visual. So the interval notation, first of all, you look at everything to the left of 4, right? So if, say it louder. 2. I'm gonna stop you there. Nope. That's right. So for the first interval, we can say negative infinity to positive 4, because that's everything to its left. And for negative infinity and positive infinity, we always use parentheses. Now, because 4 is being excluded, we use an open parentheses as well. Union, everything to the right of 4. So that will be from 4 to where? Infinity. And I also use parentheses because 4 is not being included. So that is the second example. G of x, its domain is all real numbers except when x is equal to 4. Visually, we see what that looks like. If you have one problematic input, right, you can sort of see like a little clue here. If I have one problematic input, I have one more interval to deal with. I have 2 intervals, right? Okay. Everything's to its left and everything to its right. Okay, questions on that one? The 5 is irrelevant. It's whatever causes division by 0, whatever makes that bottom, such as x minus 4, whatever makes that bottom 0. Right? Let's look at another example. So just clarify real quickly. What if I were to write this as x minus 4 over 5? Is there a value of x that makes that bottom, the denominator, 0? Say it louder. No. Your denominator is just a constant term. There's never going to be a value of x that will make the denominator 0 in this example. Your denominator is always going to be 5. So here, your domain is all real numbers as well. Domain of h is all real numbers. The numerator at this moment is irrelevant because if you look at the numerator, it doesn't contain a square root and it doesn't have fractions inside that numerator either. It's only when your denominator that you're more interested in, okay? Let's look at another example, just so that we get the hang of this. Let's say if I had k of x is equal to now 5x minus 4 over x squared minus 9. When I'm looking at the domain of my function, what do I care about? The numerator or my denominator? My denominator. I'm looking at this denominator in such a way, right, where I want to figure out the value of x that makes that bottom 0. So you can go ahead, you can write it out as an equation. You can say that you have your x squared minus 9, your denominator, equal to 0. Now, how would I solve this equation? Okay, that's one way of doing it. You can add 9 on both sides of the equation. The 9s will cancel. This will give you x squared equals 0 plus 9, which is 9. And how can we get the x by itself now? Square root. Now be careful. When I take the square root on one side of the equation, I have to take the square root on the other. But what else should I include with the square root on that right-hand side? We did it earlier in our workshop today. There you go. See, that example that we did earlier came in handy for this one, huh? So we have plus or minus the square root of 9. Now, what is the square root of 9? 3. So we're going to get two solutions here. We're going to get x equals plus or minus 3. So those solutions now are not our final answers, but they are our problematic inputs. X cannot be equal to 3. X cannot be equal to negative 3. This was one way of solving the equation. The second way, right, just note, you can solve that same exact equation using factoring techniques. So if I have x squared, if you have x squared minus 9 equals 0, you can factor this as what we call a difference of two perfect squares, right? If you notice, look at your x term. X squared, is that a square term? Yeah, is 9 a perfect square? Yeah. So what times, go ahead. That's right. You can factor this as x minus 3 times x plus 3 equals to 0 and separate it into two equations. That first equation will be x equals 3. The second equation will be x equals negative 3. So that's two ways of solving that equation x squared minus 9. You're going to use your principal square root property here, or you can use the difference of two perfect squares. Okay? All right. So now let's write this all out. So for this function, we can say that the domain of K is all real numbers such that, or except that, there you go. So that's our domain in plain English. The domain of K is all real numbers except when x is equal to plus or minus 3. So if I want to talk about visually what this looks like, we have the following. Again, we're looking at the real number line from negative infinity to positive infinity. But I could plot these two values, negative 3 and positive 3. At negative 3 and positive 3, you have open points. And then you can now draw your lines. So be careful. When I draw my line, is my line going to go through these 2 points? No, it just bypasses it, right? So I'll have one segment here, which is to the left of negative 3. I'll have another segment in between negative 3 and 3. And then I'll have another segment to the right of 3. Give me 1 second. I pull it back just a little bit. So that's what our domain looks like, from a visual point of view, and now we write out the interval. So when you write out your interval interval notation for your domain, because I have two problematic inputs now, the idea is you need 3 intervals. So starting with the very first interval from all the way from the left, you can begin with negative. Parentheses or brackets? Yep. Union. That's right. Now you look at the middle, negative 3 to 3. Union. There you go. That's it. That is your function. Uh-oh. What's up? Uh-oh. You got a question? That's right. Not included. All right. Can I do 2 more examples and then we wrap this up? So this particular example is a good exam question. Was this on your first exam? Domain of a function? Trying to find this domain? No? It will be on your second exam. Similar format. Set the denominator equal to 0, solve for x. Okay? I don't know if it will actually simplify the function, but I'll wait until you guys do factoring first in class, and then you can look at that. All right. Let's look at a couple more. Let's say if I have, let's call this p of x is equal now to the square root of 3x plus 12. The thing about this particular function is that now we're dealing with square roots, which is an even root because square is 2. So you have to exclude values of x from your domain that basically creates negative numbers. Right? So if we're excluding negative numbers, let's think about that number line that I drew out in the previous example. If I'm excluding the negative numbers, then I'm including basically 0 or positive numbers. Right? Remember, 0 is not negative or positive. So this portion of the radical, we call it the radicand, the 3x plus 12, that portion must always be greater or equal to 0. So instead of setting now an equation where you say, okay, the equation will be 3x plus 12 equals 0, it's no longer an equation, it becomes an inequality because it has to be greater or equal to 0. That implies 0 and positive numbers, okay? So 3x plus 12 greater or equal to 0, and now you solve for x. You subtract 12 on both sides. 12 here will cancel. You get 3x is greater or equal to negative 12. And then you divide by 3. So if I divide by 3 on both sides, the 3's cancel, you get x is greater or equal to negative 4. So your domain in plain English, it will be the following. We say the domain of P is all real numbers such that, there you go, all real numbers such that, the such that means that these are the values of x that we're including, such that x is greater or equal to negative 4. Visually, this is what this looks like. Here's your number line. From negative infinity to infinity, let's say somewhere here is negative 4. Now, because the inequality symbol says greater than or equal to negative 4, you now put a solid dot or a closed point. That closed point indicates that we're including the negative 4. And if you look at the inequality symbol, greater than, which direction does it point to? So does it point to the right or to the left? To the right. So that means that when I draw the rest of the domain, it should go all the way to the right. So that's your visual. And then the interval notation, because I start at negative 4 but go all the way to infinity, I know it's negative 4 comma infinity. The negative 4 this time is included, so I use a square bracket, and then I open close parentheses at infinity. Okay, one more example before we hit the road. Okay, one more example. I ran out of letters, so let's see, P, let's just use Q. So let's say if I have Q of X, now this one's gonna be interesting. This one's now combining everything that I showed in this video. Let's say if I have 5x over the square root of 24 minus 3x. 24 minus 3x. Look at an example. A couple of things happen here in this example. Sorry, I'm going to slide it up so that way you guys can see it. I know okay, my bad. A couple of things happen in this example. First of all, where is the square root located? The square root is located in the denominator. That's right. And we know that in the case of your denominator, you usually say that the denominator, you're trying to find the value of x that makes that denominator 0. Well, the issue is that because the inequality symbol states that we always include the value of x that is equal to 0, right? Greater or equal to 0. Now we're trying to take away the values of x that makes that denominator 0. There's no longer going to be greater than or equal to. It's just strictly greater, right? So this piece, 24 minus 3x, again, we're trying to look for the values of x that just makes that bottom positive. Because you have that square root in the denominator, you would have looked for numbers that would be 0 or positive. But if it's 0, that's bad for us because we cannot divide by 0. So the expression 24 minus 3x must always be a positive number, hence we just say greater than 0. And now you solve this inequality. So here's how this works. Subtract 24 on both sides. That 24s will cancel. You get negative 3x is greater than negative 24. Next, you divide by negative 3. You'll get x on one side because the negative 3's will cancel. Negative 24 over negative 3 is positive 8. But just be careful with inequality symbols here. I can't say x greater than 8 because since I'm dividing by a negative number, even if you multiply by a negative number, the same thing will happen. Multiplying or dividing by a negative number causes the sign to flip. So if the sign is originally greater than, it now becomes less than. So that is our domain. This is going to be our domain right here. So how do I write this all out? First of all, we say that in plain English, the domain of Q, that was the name of our function, is all real numbers such that the value of x is always less than 8. Okay? So visually, let's look at a graph. Here's my number line. Here is the location of 8. Now, above the 8, sorry, I have to slide this up because I know the sun is in the way. Looking at the location of where of 8, what should I put there above it? A close point or an open point? It's an open point because no longer it doesn't say that we're including 8. It says that 8 was strictly less than 8. And because it says that we're strictly less than 8, it's an open point, and then the rest of the graph should go in which direction? To the left or to the right? To the left. It goes in this direction. So we can write out the interval notation for it. The interval notation will be the following. Start all the way from the left. What value is essentially waiting for us all the way from the left? We go to negative infinity. We're going to stop at 8. Are we including any of these things? No, negative infinity, open parentheses, 8, open parentheses. And we're done. That's our interval notation. I will.